plot a frequency response using BODE's plot. Okay, so what we do here is, in this particular video, we are going to use we are going to plot the frequency response. We are going to plot the frequency response using BODE's plot. And then second thing is, the second point is, we are going to calculate, or we are going to find. So there is no calculation here. We are going to find, actually calculation in terms of magnitude and phase and all we will try to do in this particular problem. But what we do here is, we are going to find gain margin. I hope in the previous video you might have watched how to identify the gain margin and phase margin. So that method we are going to use here for this particular problem to identify what is gain margin and phase margin. And the third point here is, after finding the gain margin and phase margin, and also we try to find out what is phase crossover frequency, which is omega CG, and also we are finding out what is gain crossover frequency, which is omega CP. Okay, so we are going to find out what is gain margin and what is phase margin, along with phase crossover frequency and gain crossover frequency. After doing all these things, we are going to identify the stability of the system. We are going to identify whether the system is stable or not. So these are the three things which we are going to do for this particular given problem. Okay, now let us take the problem as mentioned here, if you see here. So let us take the problem and try to do step by step. So we have G of S into H of S equals 10 into S plus 40 divided by S into S plus 4 into S plus 10. So what we do here is, for this particular problem, the first thing what we will be working on is to do the calculations for plotting the magnitude, curve. So what we do is, we do the calculation for plotting the magnitude curve. Okay. Now step one is replace S with j omega. Okay, replace S with j omega. So if I do that, what will I get here is G of j omega into H of j omega equals 10 into j omega plus 40 divided by j omega into j omega plus 4 into j omega plus 10. Now the second step is we need to check whether the given equation or the considered equation is standard format or not. Normally when we want to have a standard format, the standard format in S domain should be in terms of k into S power z into 1 plus tz1s into 1 plus tz2s and so on, whole thing divided by S power p into 1 plus tp1z, 1 plus, sorry, not z, it is s, into 1 plus tp2s and so on. This is the standard format, time constant format. Given question should be seen that it should be in this format. Now what is k? This value, numerical value that is given in the question, this is actually k. But is this the actual k? That should be, we need to find out the actual k by looking into this equation whether it is in this format or not. Definitely 1 plus t into s, it is not having 1 here, it is having 40. So what we do is, we try to make this into a standard form. So for that reason, I'll try to first make this standard form and then replace j omega for that. So for that reason, what we do is 10 into, you take 40 common here. So if you take 40 common, I will be getting 1 plus 1 divided by 40 into S. 1 divided by 40 into S. Whole thing divided by S into, I'll take 4 common. If I take 4 common, I'll get 1 plus 1 by 4 into S. And if I take 10 common in the next term, I'll be getting 1 plus 1 by 10 into S. So this is what we get. So this should be in a standard form. That is what I'm able to tell you. So it is in the standard form. So it is 10 into 40. 40 common you should take so that it becomes in the standard 1 plus t into S form. So it is 40. If I take common, 1 plus 1 by 40 into S I will get. Similarly, these two terms, which is S plus 4 into S plus 10, that should also be in terms of 1 plus t into S and 1 plus t into S. So therefore, if I want to make this 4 to become 1, then I should take 4 common here. And if I want to make this 10 as 1, I need to take 10 common there. So therefore, what I get here is 10 into 40 into 1 plus 1 by 40s divided by 4 into 10. If you see here, 4 into 10 is 40. 40 into S into 1 plus 1 by 4s into 1 plus 1 by 10s. Now 40 gets cancelled. So finally you'll be able to get, so this I'll erase here, and I'm going to write this as 10 because 40 got cancelled and this 40 is also erased here. So finally the last equation what we get here is 10 into 1 plus 1 by 40 into S, whole thing divided by S into 1 plus 1 by 4s, 1 by 4 into S, and 1 plus 1 by 10 into S. So this is what we got. Now for that, if I replace S as j omega, so I'll just replace this equation now. Instead of writing this equation, I'll try to write this equation in standard form. So if I write S as j omega, I'll be able to get 10 into 1 plus 1 by 40 j omega divided by j omega into 1 plus 1 by 4 j omega into 1 plus 1 by 10 j omega. Now this is what the standard equation we have got. Now in the next step, now consider this whole thing as step 1 which I did till now. Consider next step 2. What we do here is we are going to find the corner frequencies. We are going to find the corner frequencies. Now as we all know that these terms are time terms. If you see here, these are the time terms. So therefore in our problem, this is one time t, this is another time, and this is another time constant. We all know that 1 over t is actually equal to frequency. We all know that the reciprocal of the time is frequency. Therefore, the first corner frequency, which I am going to find out here is this 1 over 40. So this is t equals 1 over 40, and reciprocal of 1 over 40 is first corner frequency, which is equal to 40 radians per second. 40 radians per second. Let me calculate second corner frequency, which is omega c equals t equals 1 over 4. This one, 1 over 4. So therefore, the next corner frequency which we are going to identify is 4 radians per second, because 1 over 4 reciprocal is 4. Then the next corner frequency is related to t, which is 1 by 10. 1 by 10. And reciprocal of 1 by 10 is the next corner frequency, which is 10 radians per second. 10 radians per second. Now, once you calculate all the corner frequencies, now you need to rearrange it in a proper increasing order. And that is how the corner frequency priority is considered. Now, here, the first corner frequency, omega c1, will be equal to, the minimum value out of these 3 is 4 radians. So, that will be a 4 radians per second. And this 4 radians per second is obtained due to 1 over 1 plus 1 by 4 j omega. This is a factor which is making you to get the corner frequency 4 radians per second. The next corner frequency omega c2 is, the second minimum value is 10 radians, so I'll say it is 10 radians per second. So that is the second corner frequency because that is the second lower value, and this is due to the factor 1 over 1 plus 1 by 10 j omega. Okay. Now the third corner frequency, which is omega c3, equals the next highest value, which is 40. So 40 radians per second. And this is due to the numerator term, which is 1 plus 1 over 40 into S. Okay. Now you got it. Now I just want to give you a little bit knowledge on certain factors. Now what we do is in magnitude we will try to take the slopes. In magnitude we will try to take the slopes. In magnitude plot, in magnitude plots, in magnitude plot we will try to take the slopes. Okay. Now how the slopes are defined, that is what I am saying. I am trying to say you. One pole at the origin if you have in the question. One pole at the origin if you have. One pole at the origin if you have. Then this will offer a slope of minus 20 dB per decade. Minus 20 dB per decade. Now if you have n poles at the origin, if you have n poles at the origin, means more than one pole at the origin, that is what n pole is all about. Then the slope what this offers is minus n into 20 dB per decade, where n stands for the number of poles on the origin. Okay. Now, if you have one simple pole simple pole is a pole which is giving you other than the origin. Means if you have a real pole, real value that a pole value is, then this one simple pole will offer a slope of minus 20 dB per decade. One simple pole will offer a slope of minus 20 dB per decade. Okay. Now you might get a quadratic equation in the problem, like if you might get quadratic equation in the denominator part of the given g of s and h of s. So if you have a quadratic term in your question, in another couple of videos you will be seeing me solving the problem when there is a quadratic term in the question. Then you will realize what I am saying. So if you have any one quadratic pole, if you have in the question, this will offer a slope of minus 40 dB per decade. Okay, so this slope difference, whatever you are able to see, this is very important. This knowledge is very important for us to write the resultant slope table which we write for magnitude plot calculation. Okay, so one pole at the origin will offer minus 20 dB per decade slope. N poles at the origin if you have like s power n, like s power 1, s power 2, s power 3, s cube, s to the power 4. So it says the more number of poles at the origin. So if you have such conditions, then n into 20 minus n into 20 is the slope what it will offer. Okay. Now similarly you have certain simple poles. So one simple pole will offer a minus 20 dB per decade slope. Similarly, there might be a question which contains a quadratic term in the equation. So if you have a pole which is quadratic, then that will offer a slope of minus 40 dB per decade. Okay. So this is all about poles. Now in the question you need not to have only poles. You might have zeros also. So we all know in s of s, in g of s into h of s, the numerator is always zeros. The denominator is always considered to be poles. In such case, if you have zeros into consideration, what we do is, I'll just erase here. If you have 1 0 at the origin, then the slope what it offers is plus 20 dB per decade. See, the poles will offer minus 20 dB, whereas 0 will offer plus 20 dB per decade. Similarly, if you have n zeros at the origin, then the slope what it offers is plus n into 20 dB per decade. So it offers plus n into 20 dB per decade. Similarly, if you have one simple zero, then this one simple zero will offer plus 20 dB per decade slope. Okay. Similarly, if you have finally one quadratic pole, one quadratic zero, then it will offer plus 40 dB per decade slope. So all zeros will offer plus slope and all pole will offer negative slope. Okay, keep that in mind. Now we'll go back to the question and construct the slope table. So now what we do is we'll construct the slope table next. So I think this is step 3 which we are going to do. Step 3. So what we do here is we'll construct the slope table. So in table, first thing is terms. Second thing is corner frequencies. The third part of the table is initial slope. Last part of the table is final slope. So we know that the equation was what? N into 1 plus 1 by 40 into j omega divided by j omega into 1 plus 1 by 4 j omega into 1 plus 1 by 10 j omega. So this is Okay, now let us look into step 3. So in this step 3, what we do is we will try to write a slope table in terms of different terms that we had in the question. So as we know that the question says it is 10 into 1 plus 1 by 40 j omega divided by j omega into 1 plus 1 by 4 j omega into 1 plus 1 by 10 j omega. So what we do is normally, the first thing what we do in step 3, in any problem you take, the first thing is we will try to take the value k divided by the j omega, which is the number of slopes at the origin. So the term what we take initially is 10 by j omega. So this is 10 by j omega. Now the corner frequency for 10 by j omega, if you look into the previous, go back and see, like we never had any corner frequency for 10 by j omega. But the slope what is offered because of one pole at the origin. See, there is one pole at the origin. This j omega is one pole at the origin. So initial slope that the one pole at the origin will offer minus 20 dB per decade. Minus 20 dB per decade, which is the slope offered by one pole at the origin. Whereas the final slope, we don't have anything because this is the first term which we have considered. Now the second term which we consider is based on the corner frequency that we have calculated. So we had three corner frequencies. One is omega C1, which was equal to 4. Then the second one was omega C2, which was equal to 10. So omega C2, which was equal to 10. Whereas the third one what we had is omega C3, which was equal to 40, right? So now we need to take the first corner frequency, which is 4 radians per second. Now this 4 radians per second is because of which factor? It is because of the simple pole. This is actually considered to be simple pole. So therefore it is 1 over 1 plus 1 by 4 j omega. This is the factor which generated this corner frequency 4 radians per second. Now this is a simple pole, and I told you earlier, one simple pole will offer minus 20 dB per decade slope. Now the final slope will be the addition of the current slope with the previous slope. Now the current slope is minus 20 dB. Previously the initial slope was minus 20 dB. So they both gets added up. So the final slope will be minus 40 dB per decade. Okay. Now the third term is based on the next corner frequency, which is 10 radians per second. 10 radians per second. This corner frequency is obtained because of another simple pole, if you see here. So that another simple pole is what? 1 over 1 plus 1 by 10 j omega. This is another simple pole. And this another simple pole will also offer minus 20 dB per decade slope. Whereas the final slope is the current slope minus 20 dB added with the previous slope, which is minus 40. So this will give you minus 60 dB per decade. Okay, so this is what the third term is. Now the fourth one is the corner frequency 40. Corner frequency is 40 radians per second. Now this is due to a simple zero. A simple zero which was 1 plus 1 by 40 into j omega. Okay, which was in the numerator. So this is simple zero. And that generated 40 radians per second corner frequency. And this simple zero will offer a slope of plus 20 dB. We discussed earlier about this. A simple zero will offer a slope of plus 20 dB per decade. Now this plus 20 will add with previous slope, which is minus 60, and that will give you minus 40 dB per decade. Okay. Now this is all about the slope table which we have written. Now these slopes will be considered when we plot the magnitude plot. But before plotting the magnitude plot, we need to calculate what is the magnitude value at various corner frequencies that we had. Okay. So let me rewrite the corner frequencies which we have calculated. So we had omega C1, which was 4 radians per second. We had omega C2, which was 10 radians per second. And we had omega C3, which is 40 radians per second. Okay, now these are the three corner frequencies. Now in this step, we are going to define two more frequencies, corner frequencies. One is the lower corner frequency before omega C1, and the other one is the higher corner frequency, which is after omega C3. Normally, the lower corner frequency, which we always assume, keep that in mind, we always assume lower corner frequency to be equal to 0.1 radians per second. You take any problem, the lower corner frequency is always 0.1 radians per second. Now the higher corner frequency what we consider here is anything beyond 40. Okay, anything beyond 40. I will be considering beyond 40 and 50 will be very near to 40, so I'll little bit more of 40, which I will be assuming 100 radians per second. You can also take 80 radians per second if you want. Okay, so there are two corner frequencies which we are going to define along with other corner frequencies. One is the lower corner frequency and the other one is higher corner frequency. Now what we do is we'll try to calculate the magnitude. We'll start calculating the magnitude at each one. Now coming to magnitude at omega equals omega L, which is equal to 0.1 radians per second. Okay, so this is a very important step because this is where the values which we use it in magnitude plot. At omega equals omega L, when 0.1 radians per second, which we have considered, the magnitude A will be equal to, at this lower frequency always, the magnitude of A means the magnitude A will be equal to 20 log of K divided by 1 pole at the origin or 2 pole at the origin, whatever we have. Anyway, in this problem we have 1 pole at the origin. So this is the formula for magnitude at omega equals omega L to the base 10. So here in our problem we have K, which is 10, 20 log of, this is magnitude, keep that in mind. We all know that when we have a complex number A plus JB, the magnitude of A plus JB will always be equal to root of A square plus B square. So that is what. So magnitude of K will remain to be K. So therefore 20 log 10 divided by magnitude of J omega. J omega can be written as 0 plus J omega, right? So if I say magnitude of this is, it is square root of omega square, which is equal to omega. So therefore it is omega. So therefore A equals 20 log of 10 divided by omega is 0.1. So therefore 0.1 to the base 10. And this will give me a value of A which is equal. Okay, the calculated magnitude value for this particular condition is, whatever you get is 40 dB. Okay, the magnitude value what we get here is 40 dB at omega equals omega. Now the next step is at omega equals omega C1, and we know omega C1 is 4 radians per second. 4 radians per second. So what do we get here is A equals, so when you go with omega C1, we go with the same formula, keep that in mind, which is 20 log magnitude of K, which is 10, and magnitude of J omega, which is omega. Now omega value will be equal to 4. Okay, omega value will be equal to 4. So this will give you 20 log 4 by 10, which is 2.5 to the base 10. So if you use your calculator and try to find out the value, what we get here is 7.95 dB. So here the magnitude A is 7.95 dB. So this is your magnitude A at omega equals omega C. Now at omega equals omega C2, at omega equals omega C2, which is equal to 10 radians per second. 10 radians per second. So at third omega value, okay, at third omega value, which is omega C2, we do have a formula to find out the magnitude A. For every problem, we use this formula. Keep that in mind. The steps, whatever we are doing, is same for every problem. So the magnitude now will be calculated with A equals the slope between the corner frequencies omega C1 and omega C2, omega C1 and omega C2, the slope between omega C1 and omega C2 multiplied by log of omega C2 divided by omega C1 to the base 10, whole thing added with the magnitude that we calculated at omega C1. So this formula is normally same formula that we use for every problem when we are solving. So now if you go back to the table and see what was the slope between omega C1 and omega C2, if you go down and see what was the slope between omega C1 and omega C2, now the slope between omega C1 and omega C2 was actually minus 40 dB per decade. Now this will be the slope, keep that in mind. So this will be the slope between omega C1 and omega C2, and this will be the slope between omega C2 and omega C3, and this will be the slope between omega C3 and omega H. Omega H. Okay, so minus 40 dB per decade was the slope between omega C1 and omega C2. So I will try to substitute minus 40 into this problem. Minus 40, and this gets multiplied with log of omega C2, which is 10, and omega C1, which is 4, and to the base 10. And this whole thing will be added with the previous gain, which was 7.95. 7.95 dB. So, if I calculate this using calculator, what I get here is minus 40 into log of 10 divided by 4 will give you minus 15.91, and then added with 7.95, it will give you minus 7.96. Okay, so this is your gain at omega C2, which is equal to minus 7.96 dB. Okay, and this value what you got is at omega equals omega C2. Omega equals omega C2, we got this. Similarly, at omega equals omega C1, we got 7.95. So put the box for each gain. Similarly, when we had omega equals omega L, which was 0.1 radians per second, we got A, which is 40 dB. Okay. Now the next step is, let us go to the next omega, which is at omega equals omega C3, which is equal to 40 radians per second. 40 radians per second. Okay. Now the gain formula A will now be equal to what? The previous formula was between C1 and C2. Now we'll go with slope between omega C2 and C3. Omega C2 and omega C3 multiplied by log of omega C3 divided by omega C2 to the base 10, added with the gain that we calculated when omega was equal to omega C2. Okay, now let me write the slope. If you go back to the table and see, between omega C2 and omega C3, we had a slope of minus 60 dB. So therefore, I take that slope minus 60 dB multiplied by log of omega C3 is 40 divided by omega C2 we had is 10 to the base 10, and this is added with the previous gain. Anyway, the previous gain is minus 7.96, so therefore this becomes minus 7.96. Now if I try to solve this using my calci, what I get here is minus 60, one second, minus 40 to log of. Okay, so minus 60 into log of 10, 40 by 10 is 4, will give me minus 36.123. So this is added with minus 7.96. I will be able to get minus 44.08. So therefore, the gain A at omega C3 is actually equal to minus 44.08 dB. Okay, so this is the gain at omega C3. Now, so gain at omega equals omega C. Finally, now what we'll do is at omega equals omega H, and we have assumed omega H to be equal to 100 radians per second. 100 radians per second. So if you see here, omega H was assumed to be 100 radians per second. So therefore, the slope between omega C3 and omega H is minus 40. So let us remember that. So the formula for gain A is A equals slope between omega C3 and omega H multiplied by log of omega H by omega C3 to the base 10. This is added with the gain calculated at omega C3. So therefore, the gain equals, as we knew that slope between omega C3 and omega H was minus 40, multiplied by log of 100 by 40 to the base 10, added with the gain, what we had earlier, omega C3 was minus 44.08 dB. So anyway, this becomes minus now. So minus 44.08. So this will give me the gain at omega H, which is equal to minus 40 into log of 100 by 40. Anyway, it is 10 by 4 only, which I will get minus 15.91 minus 44.08, which will give us minus 59.99 dB. So this is the gain at. Okay, now let us come to draw the BODE's plot, magnitude plot in BODE's plot. Now what I have done here is I have listed all the values of omega, which are corner frequencies, along with the amplitude which we have calculated till now. Now at omega equals omega L, 0.1 radians per second, our magnitude was 40 dB. At 4 radians per second, it is 7.95, and at 10 radians per second, it is minus 7.96, and at 40 radians per second, it is minus 44.08, and 100, it is minus 59.99, which we have calculated, and I made a list of that so that we can plot the graph. Now let me go to the graph sheet. Now this is the graph sheet. Normally, similar graph sheet is what we take. Now what I do is omega value should start from 0.1. So that is what which is very important. So I'm starting from 0.1 is omega value. So as it is a similar graph sheet, you see that there is a 10 times increment in the frequency. So it is decade. So decade means 10. If this frequency starts from 0.1, this ends at 1. So 0.1 into 10 is 1. So this frequency is 1. So this is 1 means it is 2 radians, 3 radians, 4 radians, 5 radians, 6 radians. So this becomes 10 radians per second. And this is 10 means this is actually 100. So 100 means this is 20, 30, this is 20, 30, 40, 50 till 100. And then 100 will become 1000. So this is 1000. So 1000 means this is 200, 300, 400 radians, 500 radians. Finally, you'll be able to see that the frequency will end till 10,000. Okay, 1000 into 10 is 10,000. So this is what the frequency is. So it starts from 0.1 radians per second. And this is our 1 radians per second. This is 10 radians per second. And this is 100 radians per second. And this is 1000 radians per second. And finally, 10,000 radians per second. Okay. Now this is how we mark the frequency first. Now my next job is, okay, so I'll just erase this. Okay. Now I need to divide the y-axis. Okay, I need to mention the y-axis. So let me start from here. So let me start from here. It is 20, 0 dB line. So this is my 0 dB line. So this middle line goes with 0 dB. Okay, I'll stop it. So this is 0 dB. Now I'll take from here. So this is 10 dB. So I'll just change the color so that. So this is 10, 20, 30, 40, 50. I'll just take with 10 scale. And at the bottom, I'll go with this is minus 10. I have to go with the same scale. So minus 20, minus 30, then I have minus 40, and then minus 50. Okay, now I told you this is 0.1 radians per second. At 0.1 radians per second, my amplitude is 40 dB. Okay, so therefore I'll mark 40 dB at that particular point. So this is 40 dB. So at 0.1 it is 40 dB. Okay, now my next corner frequency is omega C2, where it is 10 radians per second. The amplitude is minus 7.96 dB. So minus 7.96 dB. Now from 0 dB, see this is your 0 dB. This is 0 dB, right? So I hope it is not visible. Let me take some other color. Yeah. So this is 0 dB. So therefore, every division, so there are 5 divisions here. Each division will take two different dB. So therefore, minus 7 at 10 radians per second, it is minus 7.96. So that is what you can see in this table. Sorry, we have 4 radians per second, which is 7.95. So let us first mark that. 4 radians, it is 7.95. 7.595 will come in positive. So it is 0, 2. So this is 2. This is 4, 6, 8. So in between somewhere here, it is 7.95. So where? At 4 radians per second. So this is 1 radians, 2 radians, 3 radians, and 4 radians. So this is 4 radians. And somewhere here is my 7.96 dB point. Now what I should do is, I should join the point from 0.1 to 4 radians. Okay. So that is what? 0.1 to 4 radians. I have to mark that particular point. So I'll take a scale and I'll try to connect these 2 points. So from here till here is what I need to draw the line. Okay, so this is from omega L to omega C1, which is 0.1 to 4 radians per second. 40 dB was an amplitude at 0.1. 7.95 is at 4 radians, and the slope is minus 20 dB per decade is the initial slope. So therefore, this slope, whatever we are trying to see, this one, this is minus 20 dB per decade slope. Minus 20 dB per decade slope, where from 0.1 to 4 radians per second. And the amplitude what we had here is 7. So the amplitude what we had here is 7.98 dB. Okay. Now my next value is at 10 radians per second. You see that it is minus 7.96 dB. So minus 7.6 and 10 radians. See, 10 radians is this line. 10 radians is this line, right? So this is a line for 10 radians. So I'll go with the minus 7.96. You see here minus 7.96. I need to put a point minus 7.96 somewhere. So this is minus 2, minus 4, minus 6, minus 8. So between minus 6 and minus 8 is something here. This is the point. Now I need to join these 2 points now. Now take a scale and I need to join from here to here, this point. Okay. I hope you understood. So this is the line. Now this line will give you a slope of minus 40 dB per decade. Okay, so this is minus 40 dB per decade slope. So this will give a slope of minus 40 dB per decade. Fine. So now the next corner frequency is 10 is over. So 40 radians per second. The amplitude is minus 44.08. 40 radians per second. So 40 is somewhere this one. This is 40. See, this is 10 radians per second. So this becomes 20, 30, 40 radians per second. The amplitude is minus 44.08. So minus 44.08. See, this is minus 40 is this. 42, 44, 46. So somewhere here 44.08 is somewhere here, and I need to mark that at 4 radians per second. This is 4 radians per second. This line is 4 radians per second, and 44 is somewhere this point. This is 44. So what I need to do now is I need to take a scale and then join this point to this point. So this is the slope of, for this line, you see the next slope is minus 60 dB. Okay, so therefore the slope is minus, so this is the slope, minus 60 dB per decade. Then what we have is from next is omega h, which is 100 radians per second. The amplitude is minus 59.99. So 100 radians per second is this, minus 59.99 is the amplitude. 59, so this is 50. We have drawn this is 50 and this is minus 60, right? Now I need to mark 55.99, so approximately 60. So approximately 60 will come somewhere here. Now this is 100. If you see on top, if you go back and see, 100 radians per second is this line. Okay, so therefore I need to join from here to here, from here till here. So this is the, and the slope of this line is, the slope of this line is the last slope, which is minus 40 dB per decade. Minus 40 dB per decade. Okay. Now this is the magnitude plot which we have to do according to BODE's method. I hope you all got it, how to plot a magnitude plot. Now we need to mark the 0 dB line meeting point. Now this is a 0 dB line and this is the 0 dB meeting point. See, this point is where the magnitude plot is crossing 0 dB line. Point meeting 0 dB line, 0 dB point. Okay. Now so first of all, we'll take the same question which was initially given. So this was the question which we saw earlier while solving. So 10 into 1 plus s by 40 divided by s into 1 plus s by 4 into 1 plus s by 10. Now what we do is we will try to replace s with, j omega, which I did earlier. So we'll do that now. So g of j omega into h of j omega equals 10 into 1 plus j omega by 40 divided by j omega into 1 plus j omega by 4 into 1 plus j omega by 10. Okay, so this is what when we substitute s equals j omega, what we get. Now let us write it in the proper sense. So what we write here is, so we'll write this in the proper sense. So I'll write this as 10 into 1 plus 0.025. 1 divided by 40 is 0.025. So j into 0.025 omega, whole thing divided by j omega into, so what is 1 divided by 4 is 0.25. So 0.25, so 1 plus j into 0.25 omega multiplied by 1 plus j into 1 by 10 is 0.1 omega. 0.1 omega. As we are worried about calculating the phase value, so we need to take the angle for each component of g of j omega into h of j omega. So we need to take the angle. So therefore, angle of the value 10, angle of 1 plus j into 0.025 omega, whole thing divided by angle of j omega, angle of 1 plus j into 0.25 omega, then angle of 1 plus j into 0.1 omega. Now, if you recall the complex number calculation, we all know that angle of a plus jb equals magnitude. We know it is root of a square plus b square, which we saw earlier. When we calculate angle for complex number, it always gives you tan inverse of b by a formula, right? Tan inverse of b by a formula. But here 10 whatever we have, so 10 whatever we have is just a real. If I say what is imaginary with 10, I can write this as 10 plus 0j. So this will give me tan inverse of, so the b value is 0, a value is 10. Okay. How? Because see, a plus jb. In the place of a we have 10, in the place of b we have 0. So I can write it as 0 by 10. Added with angle of a, this you keep in mind, angle of a into angle of b is written as angle of a plus b. So both angles will be multiplied. When your product it gets, angle gets added up. Similarly, angle of a divided by angle of b, if you have, the resultant angle will be a minus b. Okay, when you have division it is subtraction, when you have multiplication it is addition. So therefore, the angle of 10 plus 0j is tan inverse of 0 by 10. The angle of 1 plus j 0.025 omega is tan inverse of 0.02 omega, 0.025 omega, divided by 1. So it becomes tan inverse of 0.025 omega. Whole thing divided by angle of j omega is tan inverse of omega by 0, added with tan inverse of 0.25 omega by 1, which is 0.25 omega, added with tan inverse of, sorry, this is 0.25, so 0.25 omega, so this is 0.25 omega, added with tan inverse of 0.1 omega. So this finally gives me all the denominator term. If I take it to numerator, it all becomes subtraction. So therefore, tan inverse of 0 by 10 is tan inverse of 0. So tan inverse of 0 is equal to tan inverse of 0 equals 0. Whereas omega by 0, anything divided by 0 is infinity. In the denominator, you see omega by 0. So this gives tan inverse of infinity, which is equal to 90 degree. Okay, so therefore, the final formula is tan inverse of this one 0.025 omega minus, see, this is in the denominator, so minus, this is 90 degree, so minus 90 minus tan inverse of 0.25 omega. This goes to the numerator, so it becomes negative, and this also becomes negative, so we write minus tan inverse of 0.1 only. So these are all angles, so that is why when angles are in denominator, when it goes to numerator, I said you angle A by B equals angle A minus B. So that is what I have written in. So this is the final formula for angle of G of J omega into H of J omega. So this is the angle we got. Now what we need to do is we need to create a table. We need to create a table where omega value and angle of G of J omega into H of J omega is the next column. So we need to create a table here for different values of omega. Okay, so we need to create a table, and after creating a table, this value should be replicated to the phase plot. Means we need to plot the phase by looking into this table. But one thing you keep it in mind, you need to substitute omega for this formula such that some value of omega should give you a value minus 180 degrees. That is very important. Okay, so because the range of omega should be decided first. So I need to do what? I need to make sure that I will be knowing the value of omega, which gives me approximately minus 180 degree. So that value of omega you should first find it out. Once you find out the omega for which the angle will give you minus 180 degree, resultant angle, the total angle of this formula should be minus 180 degree. Okay, this formula should give you minus 180 degree for certain value of omega that you substitute here. So if you get that omega beyond this minus 180, take some 7 readings. Okay, and after this minus 180 degree, takes 7 more readings. Because this is how you choose the value of omega. Because omega choosing is also very important. And second thing you need to keep in mind here is our corner frequencies. Omega L was 0.1, but our omega C1 was actually equal to 4. Omega C2, which we did earlier, was 10, and omega C3 was 40, and then omega C4 or omega H, which we took it as 100. In our previous magnitude plot discussion, these were the corner frequencies before that we actually calculated. So this corner frequency should, yeah, let us construct this table now. Actually, in this formula, if you try to work out the trial and error method, omega equals now 4, 10, 40. Between these values, if you substitute some value, you will be able to get 180. So near to 7.799. This is the omega value for which the angle is for 7.799. The angle is near to 180. Exact 180, it's quite difficult to get because exact 180 you will get it for after decimal point. After decimal point, you should go with changing some more digits so that you will get exact 180. But anyway, for this 7.799, I am able to get the angle which is 179 point. I'm able to get minus 179.76. Okay, so I'm able to get minus 179.76. Now what we do is we'll try to construct the table for omega equals 2, omega equals 3, 4, and then 5, and then 7, and then we'll continue the table calculating after 7.799. So we'll go with after 7.799 we'll go with the 10, and then we'll go with 20, then we go with 40, then we go with 50, then we go with 80, finally 100. Okay, so we'll go with till this values. So let us calculate omega value, angle value by substituting these values of omega in this particular formula. Okay, so after substituting value of omega, each value of omega for this formula, I was able to get these angles. For 2 I got minus 125.01, for 3 I got minus 139.27, so on till 100 I got minus 193.8. In between at 70, if you see here, at 7.795 I was able to get angle which is near to minus 180. So this is very important because we need to mark minus 180 point on the phase plot. Okay, now we'll keep these values and try to mark the phase values in the phase plot in the same graph sheet where we plotted magnitude plot. Okay, we'll go back to the graph sheet now. Now this is the graph sheet. Now you might ask me, like, we have plotted the magnitude plot already here. So where do we mark angle? So what we do is this side of the graph sheet, this end of the graph sheet, we'll try to mark the phase angles. Okay. Now let me go with phase angle. Starting value is minus 125. And it keeps on increasing till 205.25. 205.5 is the maximum value, and then it started decreasing. Okay, so what I'll do is I'll take minus 180 somewhere here. Okay, so I'll take minus 180 point is this. Okay, and for that minus 180, what I'll do is I'll try to draw a dotted line for minus 180. A dotted line for minus 180. Okay. So this is minus 180. Like how we did for 0 dB line, similarly we are going to draw for minus 180. Don't worry if it goes above the magnitude plot, nothing to worry. Okay, so this is my minus 180 line. Okay, so let me write that. So this is minus 180 degree line. Okay, minus 180 degree line. Okay, this is minus 180. Then the above value becomes minus 160. Then minus 140, and this becomes minus 110, 120. Okay, below becomes 200, and then 220, 240, and so on. Now let me go with frequency and omega values. See, at 2 radians per second, I have an angle of minus 125.01. So minus 125.01 is at 2 radians per second. Now with this 2 radians per second, this is 1 and this is 2. If you see, this line is actually 2 radians per second. This line is actually 2 radians per second. Right? If you go top and see, that line is actually 2 radians per second. Now in that line, I should mark minus 125.01. So in every different box, you see there is 5 different divisions in 1 centimeter. So, and the difference is 20. If you divide 20 by 5, every box is of 4 division. So minus 120 is this, 124, and somewhere in between 125 will come somewhere here. Okay, I'll mark there 120. Then what we have after omega equals 2, for 3 we have minus 139.27. So 139.27 for 3 radians. So 3 is the next line. This is 3. This is 3. So 3 means this one. This is the line where I should have something. So it is minus 139.27. So minus 139.27 will come. See, this is 140. So this is 124, 128, 132, 136, 140. So 140, 139 will somewhere just the top of this, little bit top of this. So we have 1 point here, 1 point here. Okay. Next point is for omega equals 4. For 4 it is minus 151.09. So for 4 it is minus 150.09. Now this is the line 4. This is the line 4. Now I need to mark 151.09. So 151 is somewhere between 140 and 160. So this is 144, 146, 148, and this is 152. So somewhere here, this is 151.09. So somewhere here, the point for the other one. Next, what do we have here is for 7.79, it is minus 179.76. So 7.79, so somewhere here, this is 7 and 8. Okay, this is 7 and this is 8. Okay, this both is 7 and 8. Between that is 7.79 is somewhere here. And I have 179.9, which is near to 180. This one, near to 180. Okay, fine. Next angle is at 10 radians per second, I have minus 189.16. Where is 10 radians per second? This is 10 radians per second. And I have minus 189.16. 189 is near to 190. So somewhere, this is 184, 188, and somewhere in between of this. So this line and 10 radians is this, somewhere here. So, and then after that, I do have next angle at 20, I do have minus 205.5. Minus 205.5 at 20. So this is the 20 line. Minus 205. So 20, 204, 205 somewhere near to this. This one. Then I do have next angle. Let me take for 40 minus 205.25. For 40, this is 20, 30, 40. Minus 205.25 will come somewhere here. So at 100, I will directly go to 100. Let me know should be I will directly go to 100, which is minus 193.8. At 100, it is minus 193.8. So 193.8 comes somewhere. Now this is your 100 radians per second line, this one. So 193.8, somewhere 190, 184, 188, 192. So somewhere here. So somewhere here is actually 193.8. Okay. So now what we need to do is we need to find these lines. Join these points. Okay. So I'll do that. So from here to here, draw one line. Then from here to here, this. Then first you draw it here. From here to here, draw it neatly. It should meet that point. And then from this point to this point, and then from this to this, and then from this point to this point, and then this one, and then from here go to here. So this is the phase plot curve. Fine. Have you got it? This is the phase plot curve. So if you see, I got a magnitude plot and I also got a phase plot. Now our job is to find out the phase margin, gain margin, and omega CP and omega CG, which is phase crossover frequency and gain crossover frequency. So we'll use that method which we saw in the previous video. First of all, we need to draw a vertical line which is meeting 0 dB point, go downwards, which should cross phase plot, minus 180 degree line, and so on. Similarly, you need to draw a line upwards which is from minus 180 to upwards on magnitude plot, okay, which should cross the magnitude 0 dB line, and so on. So let us do that now. So we'll draw a vertical line. Okay, let me draw a hard line with different color so that it is visible properly. Okay, right from here, this is the point, and I should take a line downwards, exactly straight. And also take the point exactly straight on top. Okay, now I need to draw one more line which is crossing 180 degree towards magnitude plot and 0 dB line. Okay, so what I do is I'll take from here, take straight line, exactly straight line, and this line should extend further, which should also cross the frequency. So draw a straight line which should exactly cross the frequency plot. And this line, that is the frequency. Okay. Now if you see here the blue line 0 dB, okay, which is giving me the phase margin. Phase margin, you see this is the phase margin between minus 180 degree and phase plot. This is my phase margin. And what is the value of phase margin? You see that this line is from here to here is phase margin, if you see exactly. So this is 160, 164, 68 and 172, between 72 to 180. So it is somewhere around 8 degree. Phase margin equals, phase margin is actually equal to 8 degree. Now 8 degree is phase margin, positive or negative? It is above minus 180 degree. See, it is above minus 180 degree. Therefore, this is plus 8 degree. Plus 8 degree. How 8 degree? See, this phase margin, if you go directly from here to here, if you go straight, it is between 172. Why 172? It is 160. Each division is of 4. So 164, 168, 172. So till here it is 172. And till here it is 180. So if you take the difference between that two values, you'll be getting 8, because 172 plus 8 is 180. Therefore, phase margin is plus 8 degree. Now if you see the gain margin, you have plotted this green line here. This is your gain margin. This is my gain margin. And it is below 0 dB line. And the value is, see, from 0 to 10, each division is 2. 2, 4, 6, 8, 10. So therefore, value is equal to 2. Gain margin is 2. As it is below 0 dB line, the gain margin is considered to be plus 2 dB. So finally, you see that I got a gain margin of plus 2 dB. I got a phase margin of plus 8 degree. Both are positive. Therefore, the system is stable. The system is stable. So I should also write the axis. In magnitude, y-axis, I took 1 centimeter equals 10 dB. While plotting the magnitude, y-axis, I took 1 centimeter. So this is 1 centimeter is equal to 10 dB. While writing the phase plot, I took y-axis 1 centimeter equals 20 degree. See, 180, 160, between that difference is 20 degree. 140, 160, between that the difference is 20 degree. So therefore, this is how the plot should be done. I hope in this video, you people are able to understand BODE's plot in detail. So you can ask me any doubt in the chatting section if you have, so that I can clear your